Hello and welcome back to Introductory Astronomy. Today we're going to cover Chapter 17, Part 1, Measuring the Stars. This opening picture right here was taken by the Hubble Space Telescope. It is a magnificent star cluster that's called NGC 265. NGC stands for New Galactic Catalog. It is a rich group of more than 1,000 stars spread across about 65 light years. This beautiful star field is part of the Small Magellanic Cloud, which is located nearly 200,000 light years away in the southern hemisphere. The total number of stars in general, even just in our local neighborhood, is virtually beyond our ability to count. Relatively few of them have been studied in detail. Yet we have learned a great deal about stars in general, as well as their ranges of properties, such as mass, luminosity, age, and even density. In this chapter, we're going to start by talking about distances within the solar neighborhood, defining luminosity and apparent brightness, figure out how we can measure the stellar temperature or the stellar size, and then I'm going to introduce a very important diagram in astronomy that's called the HR diagram. We're going to extend our small cosmic distance scale, and we're going to conclude with measuring the stellar masses in binary stars. Distance is the most difficult measurement in astronomy, and great distances require long baselines. To find the distance to a star, we must use a very long baseline. For example, the diameter of the Earth's orbit. If we take a photograph of a nearby star and then wait 6 months, Earth will have moved halfway around its orbit. We can then take another photograph of the star from the other side of the Earth's orbit, which is going to be 2 AU, from the point of where the first photograph was taken. So we end up having a baseline that is equal to the diameter of the Earth's orbit, or 2 AU. So now we end up having two photographs of the same part of the sky taken from slightly different locations in space. When we examine these photographs, we discover that the nearby star is not in exactly the same place in the two photographs, just as shown in frame B. Remember, this apparent shift, apparent, not real, so this apparent shift in the position of the star is called the parallax, meaning the apparent change in the position of an object due to a change in the location of the observer. Now remember, we covered this in detail in Chapter 4, and I gave you an everyday example where you held out your pinky at arm's length, and you saw how it appeared to shift position against some distant background when you first looked through one eye and then through the other. Now in that example, your baseline was the distance between your eyes, and the parallax was the angle through which your pinky appeared to move when you switched eyes. And of course, the further away you hold your pinky, the smaller the parallax. Because the stars are so distant, the parallaxes are very small angles, which is why it is expressed in arcseconds. The quantity that we call the stellar parallax P is half the total shift of the star. In other words, the shift as seen over a 1 AU baseline as shown in frame A. Now astronomers measure the parallax and surveyors measure the angles at the ends of the baseline, but both measurements reveal the same thing. the shape and size of the triangle, and therefore the distance to the object in question. Remember how we defined a special unit of distance that is called the parsec, and we use that in distance calculations. A parsec is defined as the distance to an imaginary star with a parallax of 1 arcsecond. 1 parsec turns out to equal 2.06 times 10 to the 5th AU, or 3.26 light years. This makes it very easy to calculate the distance to a star given the parallax. The formula is simply d is equal to 1 over p, where the parallax p is expressed in arcseconds and the distance d is expressed in parsecs. Those little brackets that you see next to the variable d and p denote that what's within the brackets is the units. So PC is for parsecs, and those quotients right there stand for arcseconds. So let's do a quick example. If we take a look at the star Sirius, it has a parallax of 0.379 arcseconds. That means that the distance to Sirius in parsecs is 1 divided by 0.379. If you put that in your calculator, you will get 2.64 parsecs. Now, if you want to convert those parsecs into light years, just multiply 2.64 parsecs by 3.26 light years per parsec, and you will find that Sirius is 8.61 light years away. Here's another example. The nearest star is Alpha Centauri, and it has a parallax of 0.76 arcseconds. How far away is it from us? Well, you start by using the formula we just talked about, d is equal to 1 over p. So take a minute to do that. And once you do, you should get 1.3 parsecs. And if you convert that to light years, you will get 4.3 light years. Now, with ground-based telescopes, we can measure parallaxes that are greater than or equal to 0.02 arcseconds. That means that we can see objects that are as far away as 50 parsecs from us. So if a star is further than 50 parsecs, we won't be able to resolve it. Again, Proxima Centauri or Alpha Centauri is the closest star to us and is part of a 3-star system. Just to give you an idea of how distances are related to something that we can comprehend rather than just 4.3 light years, if we pretend that the sun has the size of a marble, then Earth in relation to that would be a grain of sand that's orbiting a meter away. A meter is a little bit over 3 feet. The nearest star to that would be another marble, 270 kilometers away, so 270,000 meters away. Our own solar system extends about 50 meters from our marble sun. So the rest of that distance to the nearest star is basically empty. So it gives you an idea of the relationships we're talking about. Here's a picture of the 30 closest stars to the sun, our solar neighborhood. It is projected so as to reveal their 3-dimensional relationships. The circular grid lines represent distances from the sun in the galactic plane. Notice how many stars are members of multiple star systems. And all of them lie within 4 parsecs, or 13 light years from the Earth. Our next nearest neighbor is Barnard's star. Barnard's star has the largest proper motion of any star. So I would like to remind you of what proper motion is. If you photograph a small area of the sky on 2 dates that are separated by 10 years or more, precise measurements reveal that some of the stars in the photograph have moved very slightly against the background of more distant stars. This motion, expressed in units of arcseconds per year, is what we call the proper motion of the stars. So let's take a look at the example of Barnard's star. If we compare these two frames, they were taken 22 years apart, and they clearly show evidence of real spatial motion for Barnard's star, and you can see that denoted by an arrow. Now, astronomers can use proper motion to look for nearby stars. If we see a star with a small or zero proper motion, it is probably a distant star. But a star with a large proper motion is probably quite close. So here's the actual motion of the star closest to us, Alpha Centauri. The transverse component of the velocity, and transverse means perpendicular, has been determined by observing the system's proper motion. The radial component, meaning along our point of view, is measured by using the Doppler shift of lines in Alpha Centauri's spectrum. So the final true spatial velocity is indicated by the red arrow. Is the addition of the two vector velocities, the transverse velocity and the radial velocity, gives us a final true velocity, which is indicated by the red arrow. Now, we can figure out how bright a star is. And just like in order for us to judge the true brightness of a light source, we need to know how far away it is. We use a similar idea for objects in the sky. For example, from everyday life, if we don't know anything about an object's distance, the headlight on a distant truck might look just as bright as a nearby headlight from a bicycle. So we need to figure out a way to tell if something is faint because it's far away, or if it's faint because it's just really faint, even though it's close to us. So we're going to use some ideas, some terms such as luminosity. And luminosity means the absolute brightness, the real brightness of a star. So it is a measure of the total power radiated by a star. Apparent brightness, on the other hand, is how bright a star appears when viewed from our location, the Earth. Apparent brightness depends on the real, absolute brightness, but also on the distance of the star. And we can write this as a mathematical relationship. Apparent brightness, or energy flux, is proportional to the luminosity divided by the distance squared. So two stars that appear equally bright might be, one would be a closer, dimmer star, and the other could be a further, brighter one. In this picture right here, stars A and B have different luminosities, but they can appear equally bright to an observer on Earth if the brighter star B is more distant than the fainter, closer star A. Which brings me to a very important concept called the apparent magnitude scale. The magnitude scale system can be extended towards negative numbers and numbers greater than 6. This system is a little bit bizarre. It was first introduced by Hipparchos, an ancient Greek that lived between 160 and 127 BC. So here's what he did. The brightest stars, he gave them the number 1, which we call the first magnitude. And the faintest stars, the stars that he could barely see in the sky with the unaided eye, he called number 6, which is given the 6th magnitude. So if you take a look at the picture right there, number 1 corresponds to this location over here, and number 6 would be the naked eye limit. So he called number 1 the brightest star. So the whole scale was between 1 and 6. Of course, now we're able to see things that are beyond the naked eye limit, that are fainter than that, all the way to 30, which is the Hubble Space Telescope limit. And since there are stars in the sky that are brighter than the brightest star late at night, for example, our sun during the day, which is over here on the scale, so we had to actually extend this scale to the negative number. And our sun itself corresponds to minus 26.5. Full moon is minus 1.42. Full moon is minus 12.5. And Sirius, the brightest star in the night sky, is minus 1.42. Now, this is an interesting scale because it works logarithmically. So, for example, the first magnitude stars appear 100 times brighter than the 6th magnitude star. One magnitude difference gives a factor of 2.512 in apparent magnitude. So the larger the number of magnitude, the fainter the object. These numbers are known as apparent visual magnitudes, or little m sub v, and they describe how bright the stars appear to look to people observing from the Earth. And here is some common apparent brightness. Now you may ask, this is a very bizarre scale, which we inherited from the ancient Greeks. Why didn't we change it to a more convenient scale so we won't have to go to negative numbers and orders of magnitude and logarithms? Because we're using data that was collected a long time ago, and we're adding to that data, it was considered wise to keep the scale that they were using and build on that. So I know it's a little bit of a bizarre scale, but that's the one we kept. That's the one we inherited. Now, your book goes through details on how to go through this. Another way of looking at it, and this might help, is if you look at this diagram over here. So apparent, not absolute, apparent luminosity, so how bright an object appears to be, is measured using this magnitude scale, and it is related to our perception, the one we inherited from the ancient Greeks. It is also a logarithmic scale. So a change of 5 in magnitude corresponds to a change of a factor of 100 in apparent brightness. It is also inverted. Larger magnitudes are dimmer. So if we take a look at this figure right here, this graph illustrates the apparent magnitudes of some astronomical objects and the limiting magnitudes, that is, the faintest magnitudes attainable of some telescopes used to observe them. So the original magnitude scale was defined so that the brightest stars in the night sky have magnitude 1, whereas the faintest stars visible to the naked eye have magnitude 6. The scale inherited has since been extended to cover much brighter and much fainter objects. An increase of 1 in apparent magnitude corresponds to a decrease in apparent brightness by a factor of approximately 2.5. So that's a very useful comparison scale. So go ahead and study that carefully and look at the explanation in your textbook. Now, if we know a star's apparent magnitude, so how bright it appears to be, and its distance from us, how far away it is from us, then we can calculate its absolute luminosity, how bright it really is. And the way we do that is by using the inverse square law relationship. And mathematically, it's very simple. Apparent brightness is proportional to the luminosity divided by the distance squared. And this makes sense because as light moves away from a source, such as a star, it steadily dilutes while spreading over progressively larger surface areas, which are depicted here as sections of spherical shells. So the amount of radiation received by a detector, which is the source's apparent brightness, varies inversely as the square of its distance from the source. So this is very, very useful. So this is telling you that if you're on that spherical shell that's labeled 1, then you're going to see a different brightness because the brightness is divided within 1 square. If you move all the way to radius 3, so the biggest spherical shell, you see how the same amount of light has to be divided within 9 squares. So the star looks fainter the further away you go, the bigger the spherical shell location that the observer is standing on. Which brings me to stellar temperatures. The color of a star shows something about its temperature. Red stars such as Betelgeuse are relatively cool, notice relatively, and bluer ones such as Rigel are hotter. The different colors of the stars comprising the constellation Orion in frame A are easily distinguished in this photograph that was taken by a wide-field camera attached to a small telescope. The scale of the photograph is about 20 light years across. If you take a look at frame B, you see an incredibly rich field of colorful stars, and this time in the direction of the center of the Milky Way. Here the field of view is just 2 arc-minutes across, so it's much smaller than in A. Notice how the image is heavily populated with stars of many different temperatures, many different colors. So how do we figure temperature from color? Well, remember that the radiation from stars is blackbody radiation. And we know that that follows a certain pattern, a certain form, what we call the blackbody curve. As the blackbody curve is not symmetric, observations at 2 wavelengths are enough to define an object's temperature. The locations of the B, blue, and V, visual filters, with blackbody curves for 3 different temperatures are shown in this graph right here. Star A is very hot, about 10,000 Kelvin, so its B intensity is greater than its V intensity, as is actually the case for Rigel. Star B has roughly equal B and V readings, and so appears white. Its temperature is about 10,000 Kelvin. Star C is red. its V intensity greatly exceeds the B value, and its temperature is 3000 Kelvin, much like Betelgeuse. So you have to keep that in mind when you're looking at the colors of the stars. Think of the radiation from the blackbody curve. Stellar spectra are much more informative than the blackbody curves. There are 7 general categories of stellar spectra which correspond to different temperatures. From highest to lowest temperature, those categories are O, B, A, F, G, K, M, all capital letters. Now, I'm giving you 3 mnemonics to remember the spectral sequence. My favorite one is the one in the middle column that says, "Oh boy, an F grade kills me." This is one of the few things I will ask you to memorize in this class. So remember, it's from highest to lowest, so an O-type star will be very, very hot, and an M-type star will be very cool, again, comparatively. Here are the stars' corresponding spectra, starting from O, the hottest stars, down to M, the coolest stars. These are not actual spectra, which are messy and complex, but are simplified artist renderings illustrating a few spectral features. The spectra of the hottest stars at the top show lines of helium and multiple ionized heavy elements. In the coolest stars at the bottom, helium lines are absent, but lines of neutral atoms and molecules are plentiful. At intermediate temperatures, hydrogen lines are strongest. All 7 stars, notice, have the same chemical composition. And here's a nice table that puts together the characteristics of the spectral classifications. So let's take a look at spectra class O, the hottest stars. They have an approximate surface temperature of 30,000 Kelvin. They have noteworthy ionized absorption lines for helium and multiple ionized heavy elements, and their hydrogen absorption lines are faint. An example of a star that is O spectral type is Mintaka, and it is classified as O9. So notice how there is a number right after the letter. Each letter category is subdivided into 10, going from 1 to 9. 1 would be the hottest, all the way to 9 would be the coolest. So within the range of O and B spectral type, we're going to have stars that have 25,000 degrees Kelvin or 27, so they don't fall on exactly 30,000 or 20,000. So we subdivide this into the numbers from 0 to 9. Let's take a look at another example, spectra class G, approximate surface temperature 6,000, singly ionized heavy elements, neutral metals, hydrogen relatively faint. Familiar example of that would be our own star, the Sun, which is classified as G2. Alpha Centauri, the star closest to us other than the Sun, is also classified as G2. If you want to study up a little bit more on the magnitude scale, the bizarre inverted logarithmic factors of 10 scale, in your book, in more precisely 17.1, it guides you step by step on how to understand this. I also included a formula on how to convert from one to the other. Little m corresponds to the apparent magnitude, and big M corresponds to the absolute magnitude, the real magnitude. and they're related through the logarithmic scale we talked about. And I rewrote this formula. It's the same formula 3 different ways. The first one is the magnitude difference between apparent and absolute is equal to 2.5 times the log base 10 times the luminosity of the object you're seeing divided by the luminosity of the sun. If you don't have luminosity information, you can rewrite this formula as 5 times log base 10 of the distance divided by 10. If you don't have the distance and you're looking for the distance, then you can rearrange this equation for d, which is equal to 10 parsecs times 10 to the difference in magnitudes divided by 5. So it's the exact same formula, just 3 different ways of writing it, and in terms of luminosity and distance. The last part I want to talk about today is stellar sizes. So we can figure out how hot they are, how far away they are. The next question would be, well, how big is this star? A few very large, very close stars can be imaged directly using speckle interferometry. This is a familiar star from Orion that's called Betelgeuse. If you take a look at frame A, this swollen-looking star, Betelgeuse, which is shown here in false color, is close enough for us to resolve its size directly, along with some surface features thought to be storms, similar to those that occur on the surface of the sun. Now, Betelgeuse is such a huge star, about 600 times the size of our sun, that its photosphere exceeds the size of Mars' orbit. Most of the surface features discernible here are larger than the entire sun. Those dark lines you see there, they're added contours of constant brightness. And take a look at frame B. That's an ultraviolet view of Betelgeuse in false color, as seen by a European camera on board the Hubble Space Telescope. And it shows more clearly just how large this huge star is. For the vast majority of stars that cannot be imaged directly, size must be calculated knowing the luminosity and temperature. And there's a very convenient relationship between those, and it's written as luminosity, or capital L, is proportional to the radius squared, symbol for radius is R, times temperature to the 4th. And remember, the symbol for temperature is capital T. Lowercase t is for time. Now, dwarf stars have radii equal to or less than the sun's. Giant stars have radii between 10 and 100 times the sun's. And what we call supergiant stars have radii more than 100 times the sun's. So our sun, in terms of size, is definitely an average star. So stellar radii vary widely, as you can see in this picture. What you see here are the estimated sizes of several well-known stars, including a few that are discussed in your textbook. Only part of the red giant star Antares can be shown on this scale, and the supergiant Betelgeuse would fill the entire page. So notice how the sun is relatively small compared to a lot of the other stars. Now, what if you actually want to calculate the stellar radii? You can combine the Stefan-Boltzmann law for the power per unit area emitted by a black body as a function of temperature with the formula for the area of a sphere. And the area of a sphere is 4 pi r squared. So if we combine that with the Stefan-Boltzmann law, we end up having the relationship for luminosity, capital L, is equal to 4 pi r squared sigma t to the 4th. Notice how 4 pi and sigma is the Stefan-Boltzmann constant, they're all constants. So if I wanted to write this formula instead of an equality as a proportionality, then I would say luminosity is proportional to radius squared times temperature to the 4th. If instead we measure luminosity, radius, and temperature in units of the sun, solar units, then we can directly write L equals r squared t to the 4th. We covered section 17.1 through 17.4. You should be able to explain how stellar distances are determined using parallax, distinguish between apparent magnitude and absolute magnitude, and remember of that interesting scale that we have inherited from the ancient Greeks. Be able to classify stars based on their colors, surface temperature, and spectral characteristics. And don't forget the relationship between luminosity, radius, and temperature. And that is all for now.